Alright guys, here is the notes on energy. This is chapter 8. This is the last section we're going to do before the midterm. So let's get into these. Oh, one more thing. Don't forget your cars are due this Thursday. If you would like to practice or anything like that, Miss Harper has a ramp, or will have a ramp set up outside. I'm sorry, I'm not going to be at school Monday. I may not even be there Tuesday. But I will have instructions. If I'm not there on Tuesday, you still have to come to class, and I will have your assignment online again for Tuesday. Alright, first thing we're going to talk about is work. Work is equal to force times distance, so W equals FD. We've already talked about forces. Work is measured in energy. There are two things that happen in every case of work. There is an application of a force. You apply a force to the object, and then the movement of something by that force. So when you apply the force, that object moves because of the force that you applied to it, and it moves in the same direction that the force is being applied. Okay, so work is force times distance. Well, what if I just gave you a mass? Say that I just gave you a mass. Could you find a force with just a mass? Yes, because remember, mass times gravity is a force. Mass times gravity, so you would find the weight of the object to find the force. Now let's look at things that do work. Say a weightlifter raises a barbell over his head and does work. There is a force being exerted on the barbell, and the barbell is moving by the force. So there is work being done. What about holding the barbell above his head is not doing work? Why? Because it is no longer moving a distance, it is stationary. So lifting the barbell from the ground up over his head is doing work, but just holding the barbell over his head is not doing work. Alright, work is going to fall into two different categories. Number one, work done against another force. When an archer pulls back on a bowstring, they are doing work against the elastic forces of the bow. When a construction worker handles a pile driver, hopefully you know what that is, the pile driver uses a force to raise the hammerhead up against gravity. When you do push-ups, you do work against your own weight. Work is done when you force something to move against the influence of an opposing force. Often it's going to be friction or gravity. The second one is work done to change the speed of an object. The kind of work done on cars, bringing them up to speed or slowing them down. A unit for work is a Newton meter or is a joule. So energy, all energy, like work, is in joules, energy is going to be in joules. 1 joule of work is done when 1 Newton is exerted over a distance of 1 meter. Work says nothing about how long it takes to do the work. When carrying a load up some stairs, you do the same amount of work whether you walk or run. So if you walk up the stairs or you run up the stairs, you're doing the same amount of work. So why are you tired after running up the stairs in a few seconds than walking up after a few minutes? We'll talk about that later on in the notes. Alright, power. The rate at which work is done. The rate at which work is done. Power equals work divided by time. If something is twice as powerful as something else, then it does twice the work in a given amount of time. The more powerful engine can get a car up to speed much faster than a less powerful engine. So say that you have 2 lawnmowers. One is 5 horsepower, the other is 10 horsepower. Can they both mow the same yard? Yes, they can. They both can do the same amount of work. But the 10 horsepower mower will mow the yard twice as fast as the 5 horsepower motor. So this is when we were talking about walking and running up the stairs, then that's when you start talking about power. By running, you're using more power than walking. The unit of power is a joule per second, which is known as a watt. So power is rated in watts. 1 watt of power is expended when 1 joule of work is done in 1 second. In the U.S., we use horsepower, which is 1 horsepower is 0.75 kilowatts. So 135 horsepower is equal to 100 kilowatts. Alright, energy enables an object to do work. Energy is measured in joules, just like work was measured in joules. Energy comes in many forms. Mechanical energy is basically the energy due to the position of something or the movement of something. It is all our energies basically added together. You can think of it as a total energy. That's what mechanical energy is. It can be in the form of potential energy or kinetic energy or the sum of both. First, let's talk about what potential energy is. Potential energy, you'll see it as PE, is an energy that is stored and held in readiness. It's stored and held in readiness, so it's energy that wants to be used. A bowstring drawn back has potential energy. Energy is stored in the bow and can then do work on an arrow. Potential energy is found in fossil fuels, electric batteries, and in the food we eat. Any substance that can do work through chemical change has potential energy. Work is required to elevate objects against Earth's gravity. To lift something up off the ground, you're going to have to work against gravity. We have a specific kind of potential energy called gravitational potential energy. This is potential energy due to elevated positions. So it would be mass times gravity times height. So gravitational potential energy is mass times gravity times height. Looking at the formula, you can see that it does not matter how an object gets to a height it gets to, just that it gets to that height. The next type of energy I want to talk about is kinetic energy. Kinetic energy, this is the energy of motion, things that are moving. When you push something, it moves. This is kinetic energy. The formula for kinetic energy is 1/2 times the mass times the velocity squared. Only the velocity is squared here, nothing else. So because the kinetic energy of a moving object is equal to the work required to bring it to that specific speed from rest, or the work the object can do while brought to rest. You see the velocity is squared, so if the velocity is squared, the kinetic energy is quadrupled. So 2 squared equals 4. Consequently, if it takes 4 times the work to double the speed, also an object moving twice as fast takes 4 times as much work to stop it. So it's not a 1-to-1 ratio here. So what I want you to take from here is this, that work equals kinetic energy. We can say that work equals kinetic energy. We can also say that work equals potential energy. It's just not moving yet. It's the potential to do work. So we're going to work problems with this in the work sheets that you get later this week. So our work energy theorem, that work equals energy. Work changes kinetic energy. If no change in energy occurs, then no work is done. Likewise for potential energy. Whenever work is done, energy changes. More important than knowing what energy is understanding how it behaves, how it transforms. And I'm going to show you a little thing about transforming energy in just a minute. Alright, here's a little scenario for you. As you draw a slingshot back, the rubber band has potential energy. When released, the stone has kinetic energy equal to the potential energy. It delivers this energy to its target, a wooden fence. The slight distance the fence post is moved multiplied by the average force of impact doesn't quite match the kinetic energy of the stone. The energy balance is not right. If you look, the fence and the stone are warmer. How much warmer? By the energy difference between the two. It changes from one form to another without net loss or gain. What we're saying is whatever energy you start with will equal the energy you end with. It might be a different form of energy because when I say it got hotter, that means heat was involved, and heat is a form of energy, and so we have to take that into account when we try and balance out our energy equations. Law of conservation of energy. Energy cannot be created or destroyed. It can be transformed from one form to another, but the total amount of energy never changes. This is one of the key concepts for the entire year that you need to know. The law of conservation of energy. And I'm going to draw my little pendulum thing here. It says to draw. You know what a pendulum is? A little thing that swings back and forth. You can see them on grandfather clocks and stuff like that. So this is a pendulum that's swinging back and forth. Let's say it's swinging, starting out going this way. Let's say that I hold it up here at the top. What kind of energy do I have? Well, if I'm holding it up at the top, is it moving? If it's not moving, it can't have kinetic energy, so all of the energy would be potential energy here. It starts to swing down now, so it is moving now, so if it's moving, it'll have kinetic energy. But can it still go lower? Yeah, so it has to have potential energy too, because it isn't to its 0 point yet. Gets all the way to the bottom. Can it go any lower than this? Nope. So it's all kinetic energy at this point. Starts to swing up. Swinging up, we have potential energy again and kinetic energy again. Up to the top, back to potential energy. So it just transforms between states. It'll go potential, kinetic, potential, back to kinetic, and so forth as it swings back and forth. So that is conservation of energy. Basically how it goes from one form to the other, but it'll always add up. Because let's say that this is 100 joules right here. I have 100 joules of potential energy. Well, if it's halfway between, I'd have 50 joules of kinetic and 50 joules of potential. Down here, it's back to 100 joules, but it's all kinetic. Here we have 50 joules of potential and 50 joules of kinetic. And then back up here, it's 100 joules again. Transfers between states, all the total energy stays the same. All right, a machine is a device used to multiply forces or simply change the direction of a force. We're going to talk about parts of several types of machines. A lever is a simple machine, a bar that turns about a fixed point. If you think of a teeter-totter or a seesaw, something like that, the lever is going to be the bar across, and we're going to talk about a fulcrum in a second, is the pivot point. Work input will equal work output. Remember, work is force times distance, so it's force times distance input. This should be a subscript, and force times distance output. All right, the fulcrum is the pivot point for our lever arm. The lever can be relatively close to the load. There's a small input force exerted through a large distance will produce a large output force over a corresponding distance. Or a lever can multiply forces. No machine can multiply work or energy. Think about it this way. To do work on a door, we have a pivot point on the door on the left-hand side. You usually press on your hand as far away from the pivot point as possible, because by doing that, you're creating a longer lever arm. That's the distance from the pivot point to where you're applying the force. So if you put your hand on a door to open it and you're far away from the pivot point, it takes very little force to open the door because you have a long lever arm. Well, if you shorten the lever arm, say you put your hand right by the access point and try and push open the door, it's going to take a much greater force to open the door. So it's going to take the same amount, both force times distance, to do the same amount of work will be done. It's just, do you want the length, the lever arm to be long with a small force, or a large force with a short lever arm? You always want to go with the longer lever arm. Mechanical advantage, that's the ratio of output force to input force for a machine. Alright, a pulley. A pulley is a kind of lever that can be used to change the direction of a force. So if you have a single pulley, if you pull down on the pulley on one side, the other side of the pulley is going to go up. We're not really going to talk about pulleys. I just wanted you to really know what they were. Okay, efficiency. You will never have 100% efficiency in anything that we do. Some energy is always lost as heat, and heat is a type of energy. We call this dissipated. We may put 100 joules of work onto a lever, but only get 98 joules of work out of it. The lever is said to be 98% efficient. So efficiency will be equals the useful work that output divided by the total work input multiplied by 100. An inclined plane is also a type of machine. It is easy to slide up an incline than lift straight up. So it's easier to push something up an incline than it is just to pick something up and set it down. And this is our last slide. Another way to find efficiency is the actual mechanical advantage divided by the theoretical mechanical advantage. It will always be a fraction less than 1. Every living cell in every organism is a machine. Like any machine, living cells need an energy supply. Most feed on hydrocarbons that release energy when reacting with oxygen. There is more energy stored in a molecule of food than there is in the reaction products after the food is digested. We don't use up all the food, all the energy in a food. We expel some of it. We don't use everything up completely. So that's the notes over work and energy and power. You'll have workbook problems to do, and hopefully I will be in class on Tuesday. If I'm not in class on Tuesday, I will get you work to do, and it'll be posted online.